get students saying that the pi bond here moves here. And that doesn't make sense because we're now taking those electrons away from the oxygen. That was our initial problem that we don't like. Okay? So the language and what they're looking for as an answer, I think, can lead to student misconceptions. Okay? What's drawn here, I think, satisfies the question based off of my experience with what we're trying to do with Lewis structure or with resonance. It's not showing the full extent of the resonance options, and therefore I don't think it addresses the answer. Okay? So I would say it's not good enough. The question's just vaguely written. Okay? What they could do to fix it is that there's multiple resonance structures. Draw the two resonance structures. Ta-da, there's one. Where's the other one? All right, well, we'd look at that. We could say we could move the lone pair on the oxygen, but the only place we could move it would be right back to where we started. So instead of looking at the lone pair, let's look at the other pi bond. If we move the other pi bond, we're now moving it to this space. There's our new pi bond. And then our carbon down here would be positively charged. So to me, what I think is happening is someone said, this is the answer I want. What is the question I ask to get people to go from what's in black to in purple? That is a very bad way to write a question, but there aren't a lot of good ways to do this either. Okay, so they are kind of stuck in a box on this one. But that's probably what they're asking for. You're making it sound like you got it. Yeah. Okay, and so that's what they're fishing for. In this particular case, I would argue, yeah, the pi bond is in a new space. We have a pi bond in a space that there was not a pi bond to begin with. Does that work? Okay. And you said you had more questions?
Just 13. I'm pretty sure like in my mind I have it right. But when I try and draw it, it connects two of the hydrogens I'm trying to draw. But they're not supposed to be bonded together.
So line bond structure for 2, 3, 4, 5-methyl heptane. I'll say all of their structures that I can find within the program are all, I think, a little on the too simple end. So I would recommend that if you work on nomenclature, you try and find some that are a little bit more complicated. Instead of methyls, they should be ethyls or propyls or butyls. They should get some other kind of names in there just for the record. So when trying to draw a structure from a name, where you should start is the main chain. That hept part. Hept means 7. Okay, so we could draw it out by doing our tap. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Fudge. 7. We should now have 7 carbons. Okay, we got 7 carbons. The next thing I would address is the ane. The ane is being our hybridization. That's saying all single bonds or sp3 hybridizations. Okay, so in our backbone, they're all sigma bonds, so we're okay. Next part is methyl. Methyl, or meth, really, is 1 carbon, and the YL means it's a substituent. So we're looking at a CH3. It says tri, which means I have 3 of them. Now it's the question of where do they go. That's going to be kind of the next placement, 2, 3, and 4 position. So what I would go through and do is at the 2 position, I would drop in a methyl. So I could go here, here, and here, where I've internally numbered in my head 1, 2, 3. Are those clear enough?
Yeah.
5, 6, 7, and then that would be my drawing. Test experience, just to give you an idea on this, what we've done is drawn this from left to right. More than likely, multiple choice is going to show up as multiple choice, not as a show your work or draw something out, just because there's lots of different ways you could screw things up drawing it out, and I don't want to deal with how to assign points. I've done it once, and it got down to like tenths of a point for things. It was stupid. Okay? So it's going to be strictly multiple choice. The way we've drawn it is reading it left to right. So you could do this structure knowing relatively little about organic chemistry, and if the answer choices is written left to right, you could stumble accidentally into the answer. Does that kind of make sense?
Yeah.
Which means if you are trying to practice test systems and you're trying to think about how someone's going to present a test question, don't present it left to right, because that left to right presentation, people could accidentally get correct. The point of a test is to understand what people know. So very often what you'll see is flips off of that. So instead of numbering it left to right, you should number it right to left. 1, 2, 3, 4, 5, 6, 7. And then that means our methyls would be here. That doesn't change anything about the structure, but it changes how it's presented in the multiple choice. Does that make sense? You laughed a little bit. Do you get it?
No, they counted that as well.
Bullshit.
That's what I tried it and they counted. I got it right the second time, but
I also tried that and they
It was
said it was
wrong.
wrong, yeah.
that's why. Yeah. So it wanted it 1, 2, 3. Yeah.
I wanted it left to right.
Yeah. And I did it the other way because I watched your video and you said I should probably do it from right to left.
Do you have it pulled up?
I have it right now. That's correct. I did it right. But I don't have the
And you don't have the ability to see your old answers.
No.
I want to look at that, and I'm going to ream them on that. That is that is flabbergastingly problematic.
I could have swore
That-
it was wrong. That's why I laughed.
Yeah.
Yeah, because I was
So
like,
it was
I
like
know
this
it's
system.
right.
Yeah. I will look into it, and I will see what's going on with that, and hopefully we can resolve that as a problem.
I mean, we know that there's multiple ways to do it.
Yeah.
Do we really want to float that? Do you all recognize that there's easily multiple ways to draw a structure and still be correct, particularly when entering it into a homework system that says you are wrong?
I don't
Okay.
like being set up.
So I'm going to say that that is a false assessment. I understand that you're starting to recognize those pieces. This is a very simple issue for it to be appearing with. If it's doing it wrong here, it's going to do it wrong when it really frickin' matters. So I need to look at it and
Okay.
probably write an email and then let it sit for 24 hours before I send it so I can remove language. I need to know. That's the number one thing. You were confident that you were right. That's great. That's phenomenal. I need to know, ideally, when it happens, so I'm not exploding at the whole class. Because I don't want you all to feel like I'm attacking you. I'm not attacking you. That's a problem with something else. And if this is a continued problem, we're not using the software. Okay. Do you have another question?
No, that's
You're like, no, with that, I'm just going to keep my mouth shut for the rest of the semester. Okay, anybody else have any questions about what they were encountering within Active? And yes, things like that can manifest. That particular issue is not one that should manifest, and that's very problematic. But there's other things that are formatting issues that might be going on with that question, in all fairness. So I have to dig into it and see if it's a formatting issue or if it's a legit, their software is flawed.
I had questions about Newman projection.
Newman projections, yeah, which is one of the things I wanted to talk about today.
Because I was confused. Like, I don't remember going over that.
Yeah, so the homework question was written for it to, or the
Okay.
set was written to be due this past Sunday, but the due date was wrong, right?
Yeah.
So it's written for following Sunday. It was written because we're supposed to have covered all that because our exam was supposed to be this week. So I was projecting where I thought we were going to be, and we just weren't there.
Okay.
So we'll talk about that today, and that's what I'm kind of playing around with up here. Okay. Where we ended kind of last week, or actually got to content-wise, sort of for Lynette's sake, because she missed class, and a couple other people asked to go over it again, was our functional groups. Right? So our functional groups is just that we're making bonds now between different atoms. Because those different atoms have different electronegativities, that changes different reactivities. Because the reactivities are different enough, we name that functional group. So this chart is just saying, well, if I have a single sigma bond between these two atoms, this is what I would call it. If I have a single bond between these two atoms, that changes the name because the functionality is different. These are kind of what I would call our core functional groups, okay? And even within these, we'll refine them a little bit. So we're looking at alkyl, amine, hydroxy acid, and that acid's a bit dangerous of a statement. Alkane, amines, alkoxys, halos. And so some of those names we'll see on the next slide, but really what these are just are kind of core functional groups. When I now put those core functional groups together, that can create new functional groups. Those new functional groups, if they have a different chemistry, then also get a different name. So it becomes very helpful to be able to look at a drawing with a bunch of different atoms and to be able to say, oh, that has this functional group. I know that functional group is something that has some particular chemistry. We don't know what that chemistry is yet because we haven't talked about reactivity. All we're looking at is how do we build out these pieces so that we can identify those pieces later on. So really all we're trying to get at here is that these are our core functional groups and you need to be able to identify them. That's it. Right? You should be able to draw them, all that fun stuff, but you aren't concerned about reactivity. You aren't concerned about necessarily where all the electrons are. You're just concerned about when I see this shape, I know that's an ether. When I see this shape, I know that's an aromatic. When I see this shape, I know that's a carboxylic. Kind of, sort of? Okay. Feel a little better? Nate? Maybe? Okay. Within this, there's some extra pieces of information that can sometimes confuse people. What functional groups have I drawn? I would argue you can call two functional groups out of this, out of that drawing. There's really only one core one. What's that? Ether. Yeah, I was conveniently trying to draw it next to it. Okay, there's our ether. It's an oxygen bonded on both sides by carbons. Note the carbons are implied within our drawing. We have to remember that. Why aren't we seeing all this wedge dash stuff? Because it's not necessary to show it here, so it doesn't get shown. That wedge dash stuff isn't saying it's bonded out to another carbon. It's just saying it's bonded out to something. I don't really care what that something is. All I'm saying is the core functionality is carbon, oxygen, carbon. Okay? When I look at alkenes, the core functionality is carbon, double bond, carbon. I don't care necessarily what's connected out there on the other ends. The core functionality is still an alkene. Kind of, sort of? As we'll do this, or as we move through, just like we talked about earlier with drawing Lewis structures, you'll see formulas. Those formulas can tip you off to those functional groups based off of their certain patterns. Okay? The formulas provided here are misleading because those formulas are now defining what those atoms are. Does that make sense? So I can't draw just a formula for an alkene that would allow me to differentiate it from an alkyne if I didn't add some extra characteristics. Okay? So the formulas are more examples, not a representation of the core functional group. Kind of, sort of? Okay. With practicing this, what you should, and I think there's questions, if not in Active 2 and Active 3, where you should see, and Active didn't ask the questions I wanted, you should see a large structure and say, what are the functional groups present? And you just go through and you find them. Because an individual structure could have tons of different functional groups. So you have to piece out what functional groups are present. For the most part, when we talk about our reactivity, we're only looking at a single functional group at a time. We aren't adding a whole bunch of them in there. Why? They can compete with each other. So we want to simplify our overall reaction schemes to make that easier to understand. If you were in a more advanced class, we'd start to throw multiple function groups into a structure and have you run reactions where, oh dang, that one's problematic. I need to ignore that one somehow or hide it so the reaction doesn't get in the way. Right? Make sense? Okay. So at this point, if we think through kind of what we've done, we've talked about, I'll come back to this in a second. We've talked about Lewis structure, how we build our molecules. We talked about the simplifications of those Lewis structures. We've now talked about hybridization of those atoms, which helps us to explain where electrons are located. We haven't really said why that's necessary super yet. We did do a little bit of why on that. For instance, the alkene with a pi bond, why is it important to know where the electrons were for the pi bond? You guys remember? We had a pi bond, where were our electrons located? As a hint, pi begins with the letter. You all know how to spell pi, right?
The other word.
P. It's p orbital. Where are the electrons for a pi bond? They're in a p orbital. Our p orbitals are kind of on our axes. And if we look at a pi bond, what's a repercussion of our hybridization theory? I'm not allowed to rotate, because if I rotate, I break the pi bond. So knowing where our electrons are can help us predict something about the chemistry or physical properties of those functional groups. So that's why we need to talk about our hybridization. Right? Once we dealt with hybridization, we then officially moved into our functional groups. We now have all of this information of what our drawings are. We have our functional groups. Now we should know something about how we name those so that we can talk about them, theoretically. How much of you guys talked about anything we've done?
Talk to myself.
Right? But when you're talking to yourself, are you actually using all the organic terms, or are you drawing out structures and saying, well, what does this part mean? What does this part mean? You're looking at the drawings and interpreting the drawings. Nomenclature itself is really only useful if you're communicating the language either with another person or writing something out. Then it is absolutely powerful and useful, like typing things out. Okay? In this day and age, our drawing abilities have gotten so great with new advances in technology that I would fully expect that we don't need to name our compounds, because we could just draw the structure and say, hey, this is what I'm working with. I don't need to name it so that you can then take the name, turn it into a drawing on your page. I can just email you a picture and say, this is what I'm working with, and now we're both on the same page. Right? So I have big issues with nomenclature being a necessary thing to teach because of that. Okay? Add to it, nomenclature is just a list of rules. Okay? The examples I usually run with is, what's my name? Why? Why is my name Mike? Is it because I have brown hair? Is it because I'm wearing shoes? It's a random, arbitrary system for why we picked names. Okay, that's it. Okay? When we deal with nomenclature, it's ultimately the same thing. It's a random, arbitrary system, but it's very hard to use a random system to talk about molecules, so we created a rule set to help us generate a single name for compounds so that we can have a better conversation about it. This means you have to know the rule set to be able to explain the name. If you don't know the rule set, you can't name it. Period. Okay? And as I believe we did as an example, you could use a name that doesn't follow the rule set, that gets to the structure, but is still considered wrong because you didn't follow the rule set. Okay? So there's a lot of kind of stacking things that make nomenclature frustrating to deal with. This slide becomes the critical slide that I think you should really kind of commit to memory. How much of it? All of it? As much as you humanly can. Okay? Number of carbons, super important. We're always going to encounter that through our main chain. How to name the functional groups that are present within that. That's dealing with all of those functional groups. This is why we need to know what our functional groups look like, so that when I see the structure, I can reference the name here, so that I can then reference how the name processes. What are we talking about in processes? You'll notice our ethers are an oxy with a dash, halo with a dash. Okay, what is that meaning? These are so low in priority that they will never be the end of a name. Never is a loose term. But they're never the dominant part of the name. So when we did that example in the 234 heptane, the root of the name was heptane. There it is. That's the end of my name. Everything else is hangers on. These functional groups are so low in priority that they will always come in the front of the name. They will never end it because we got that dash. So that dash is trying to show. We go up to alkanes, you'll note we do have one where the dash is in front and it ends with ane, with the E. That's because the alkane can end a name. You'll see an arrow. Sorry, I know that doesn't look like an arrow. You'll see a box, which is supposed to be an arrow. Okay? Copy paste with Google, fun stuff. Okay? That box is supposed to say an arrow. And what that's saying is that if I have an alkane as my primary functional group or as my backbone, but there's a higher order functional group present somewhere else in the molecule, say like a ketone, well, the ketone is a higher priority. So I can't end in ane because the ketone's supposed to end in one. So what happens? I switch it and I drop the E part of it and the one comes in. So I'd get ane-one. Why are you laughing at me? It just, okay, I can accept that. Ane-one is a little weird. Okay? Can make it worse. Could have done the aldehydes. As you process that one, that was good. Okay. So that's what's happening within each of these kind of boxes. Is they're saying, what's your highest priority functional group? For the most part, we're sticking single functional group order. Okay. You may see an alcohol show up with the alkanes. Okay. The alkenes and the alkynes, you'll notice, are 7 and 7b. That's because they're ultimately kind of tied. Ethers and halides, again, tied. Okay. What are those tyings in reference to? Both the ending of the name and when you assemble everything, you have to put the name together in alphabetical order. Okay. So that alphabetical order is now going to be based off of some of that naming and all of that priority stuff. So we have to kind of process through all those pieces. Okay. So functional groups, we've got our suffix. That's our first dash line. Higher priority functional group. If another one is present, then we lower priority switches out to the alternate and we use the higher priority for the rest of the name. Okay. General rules, find your longest carbon chain. Everybody remembers longest carbon chain, which is great, but almost everybody forgets the last part. It has to contain the highest priority functional groups. Okay. The example that actually just showed up in the full OChem class that everybody was struggling with was if I drew something like this. Okay, very clearly left to right, that's the longest carbon chain, right? Everybody okay with that? Is it still the longest carbon chain?
If that's a substituent.
If that's a substituent, because we've spent the time to memorize all of our functional groups, we know that functional group is the... Come on, you had like 5 minutes to memorize all those on the previous slide. That's an amine, so we'd go to our list and see there's our amine. Amines are higher in priority than our alkanes, which means the longest carbon chain must include the amine as part of it. And now I have to decide, it looks like it's longer to the right. That's now my longest carbon chain. It's shorter than the previous one I had, okay? But it's the longest carbon chain that contains the highest priority functional group. That becomes a huge caveat on that. Kind of, sort of? Okay, so before we get to nomenclature, we have to know our functional groups so that we can find those bits. Yes?
Why is that an amine?
Amines, what is an amine? It's a nitrogen connected out to things. So let's see if I can backtrack. I shouldn't have picked an amine because I'm pretty sure in this thing, yeah, it's not super obvious. Okay, we have a nitrogen connected out to things. Carbon, we already had that carbon, right? And then it's connected out to what? Carbon, comma, hydrogen, meaning it could be carbon or hydrogen. So on that example that I showed up, ballpark, really ballpark, we have the N of our amine connected out to the, whoops, not that one, to the C of the example functional group, then connected out to a hydrogen. There's a hydrogen, and then technically a second hydrogen, because it says 2 here. And that's the amine. Make sense?
That was a number, the comma.
Oh, no. Yeah, it's a comma. Make sense? And that's why this can be very confusing to deal with. You have to be familiar with what those structures look like. That's why we have to talk about drawing. That's why we have to talk about all those things first to try and build out to it. The amine is a tricky one because you can have what's known as a tertiary amine. Tertiary meaning the number of carbons it's bonded to. Tertiary being how many carbons? 3. If all 3 of those are carbons, it's a tertiary amine. If 2 of them are carbons, it's a secondary amine. If only 1 of them is a carbon, it's a primary amine. Okay? So it's referencing the number of carbons connected when we reference primary, secondary, or tertiary. Okay? Why is that important? It changes the chemistry of the functional group. Okay? And we'll use that primary, secondary, tertiary naming system, if you will, later in the semester as well. Okay? So we find our longest carbon chain. We identify the highest priority functional group and the substituents. We then have to define the location for each. The location is our 1, 2, 3, 4, 5, however many we need, but we have to number it so that our highest priority functional group gets the smallest number. So it's not left to right, top, bottom, right, left. It's lowest number with the highest priority functional group. Then you number it out. Okay? Once you've done that, you now know where all your individual pieces are. You know what the names of those pieces are. Officially, your last part is to put all of those pieces together, okay, according to alphabetical order and yada, yada, yada. Kind of, sort of? Make sense? Yes.
I mean, I've memorized like the main substituents, but if there's others, like how am I supposed to know that it's not on here? Like what are the important ones to know?
So our substituents are named effectively the same way that we would name our main structure.
Okay.
So for this class, your substituents are probably going to sit as meth, eth, pro, bute, and that would be the end of it. Okay? If we added any other element to that, what happens? That's now a higher priority functional group, which then means it's not a substituent, it's part of the main chain.
Okay.
Does that kind of make sense?
Yeah.
And you can make some really complex effed up structures that are going to break all of these rules. Absolutely. Don't. Stop. Don't make it more difficult than you have to. Okay? And that does become one of the challenges that you will see if you go out into the internet to find nomenclature questions as general practice. Because they are going to go very haywire on you, or can go very haywire very quickly. So you want to keep relatively simple names. Okay. How do we decide what are simple? Ideally, that's where I would be providing practice. So we get things like this, okay, and we can go through and name the pieces here. See, give me a sec. These are okay as far as substituents. These ones would be okay to process out. This one will get a little bit hairy, but we can talk through it. Yeah. Kind of, sort of. We'll name a couple of these to where I would like you to get, and then we can talk about it. Yes? Yeah, see? Thank you, Jennifer.
Is it supposed to be EDD?
These ones, yes. Yep. Those are all the same priority.
And it's always substituent first, functional group last in the name.
Highest priority functional group last, yes.
Okay. So the highest priority is in the back, and the least priority in the front.
Yes.
Okay.
So, lower left, we want to find our longest carbon chain. Okay, that contains our highest priority functional group. What functional groups do you see within the lower left? Floats in kind of a weird gray area. Some people don't call it a functional group. It's alkane. So there's no halogens, there's no ethers, there's no heteroatoms. So that means pretty much all of our list is irrelevant, and all we care about is that it's an alkane. So now all we got to do is find the longest carbon chain. So where do you see the longest chain? Is it right here? No. Is it right here? I mean, we've added 2 more carbons as opposed to the 1 there.
No.
Is it right there?
I think so.
So that's now my longest carbon chain. So what I would like you to be able to get at is, number 1, what is the longest carbon chain? Good. You've now identified it. You should also be able to name it. So what would be the name of that root carbon chain?
It's 9, right?
I don't know. I can't count. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9. So what I would expect you to tell me is it's none. Yes. Alkane. I'm going to delete it all. If we go back to kind of here, our priority of naming, that's not very helpful because we don't know what each of those things are. That's where we'd go back to the functional groups to memorize which of those functional groups closest match. So our alkanes is just carbons with single bonds. Our structure was carbon with single bonds. Alkyl halides, I need to see a halogen. Was there a halogen in it? Nope, so it's not a halide. Alkenes is with a double bond. Was there a double bond? Nope. Alkynes, triple bond. Was there a triple bond? Was there a big old ring? Was there an oxygen? Was there a nitrogen? No. All of those are wrong. The only one left is alkanes. So this is why people typically don't say alkanes as a functional group, because it has to exist. It's the lowest level that we can have. Does that help? So highlighting it out again. So I can envision a question saying, what is the longest carbon chain, or what would be the name of the longest carbon chain as a multiple choice, right? And what you would be selecting would be the non ane. Because the non is the 9 carbons, the ane was that it was an alkane. Note that I put a dash in there. A dash is wrong. I'm putting the dash in there to help highlight that kind of difference, that those are different parts of the name. Make sense? Okay, so that gives us our main chain. That's a potential multiple choice on this. After that, have we identified everything within this molecule? Nope, we're still missing some pieces, right? So those pieces would be here, here, and here. Okay? Those are atoms that I have not highlighted, so I haven't accounted for them. How many atoms are in the green circle?
4.
Yeah, I knew you were going to say that. Damn it. How many carbon atoms are in the green circle? 1. Why do I only care about the carbon atoms? That's the naming system. 1 carbon chain is called math. Whoops, I wanted green. Because it's not part of the main chain, I could also add by, and I'll throw in the dash again just because it's a different piece, the YL saying it's a substituent. How many atoms are identified in the purple circle?
2.
2. And I said it again. How many carbons are identified in the purple circle? 2. What is 2 carbons? F. Again, substituent, YL. In the blue circle? 2. Again, F. And I immediately started to write the YL. F with our dash YL. I now need to specify where each of those substituents is located in my molecule. Okay? I want the lowest possible numbers first. So I want a number in the way that gets me the lowest first number I find. If I number it in black, 1, 2, 3, 4, okay, that would get me the 4 position for the ethyl. That would be my very first one. 1, 2, 3, I have the methyl. What does that mean? Numbering it right to left-ish is more appropriate than left to right. And it should be the red numbering system, not the black numbering system. I would ditch those. 3, 4, 5. I would probably stop numbering at 6 because, why am I numbering?
In order to put the substituents at a place.
To know where the substituents are. I don't have any more substituents after 6, so I'm not going to worry about that one. The blue one is located at position 6, so I could call that 6-ethyl. The methyl is located at position 3, so I could call that 3-methyl. The dash there is actually a real dash. And then the ethyl is located at position 4. What I've done is now named all of the pieces of the whole thing. As far as that rule set goes, I think it was 1 through 3. The thing that I haven't done is assembled the whole name. The assembly of the name now has to go by alphabetical order, which we'll address here in a second.
Could you explain why you numbered right to left?
Right to left, if we number the other direction, left to right, 1, 2, 3, 4, my first substituent shows up at position 4. If we use the red numbering, 1, 2, 3, my first substituent shows up at number 3. Which number is smaller? 3. That's why we numbered that way. Okay? In this case, all the functional groups had the same priority, so there was effectively a tie there. I would have to just go by lowest number. If one of them was a higher priority, that one needs to get the lower number. So now when we go through to assemble the whole name, we'd start with all my substituents, and I want to order alphabet first. So if I look at my substituents, we have eth versus meth. Which comes first in the alphabet? E, so I need to start with ethyl. Okay? Here's the fun part. I need to specify the location of that ethyl. Wait, which ethyl am I referring to? And for those of you like looking at it, you're referring to the purple one because you're pointing at it. But if we're at home, we can't see that because we can't gesture at it. We have to remove the gesture and say, which ethyl am I referring to? Well, I don't know. So my name has to reference both at the same time. So I would say 4, 6, because there's an ethyl at position 4. There's an ethyl at position 6. How many ethyls are there? 2. I also have to add that word in there. So I have to say 4, 6 dash diethyl, because there's 2 ethyls. Okay? Those people, isn't that redundant? Yes, it is. We still do it. Okay? Diethyl. Now I've got my next substituent. Dash 3 dash methyl. And then my overall ending name, nonane. If I called this 3-methyl-4,6-diethyl nonane, we'd still be able to draw the structure, but we swapped the order of those 2 substituents. We're now wrong because the rule is they have to go alphabetical. Okay? You will encounter lots of exceptions and lots of ties and lots of nasty things when it comes to nomenclature. In a standard class, I would say just reference the textbook and hope that they told you the rule. I can't do that in this class. If I ask a question where you don't think the rule was provided, absolutely speak up and challenge. Okay? I'll try and pay attention to it too, but mistakes can happen.
Just really quick, so every substituent you have is always going to end in that YL?
Every substituent is a YL. Not every substituent is a YL.
Is it everyone that we're going to look at as a YL?
Probably.
Okay, because there's
That's
also
probably
like,
true.
on that
Oxos.
slide. Yeah.
Oxo, hydroxy, and amino don't have YLs. They end exactly like that. So if you had an aldehyde that wasn't highest priority, it would be, you would call the position it's at 3 oxo nanoic acid, which doesn't exist as a structure, but those substituents, if they aren't the highest priority, don't get called with the YL. The YL only applies with everything else. And I will say you can push and break this. I would recommend you don't. Try to avoid breaking it. So the rest of this was play posit sides. The intent here was trying to go through and look at some names, look at how they break down. We've got the color coding in there to try and call attention to each of those little bits of information. Make sense? Questions about any of that? Okay. Oops, I do kind of want to talk about this. When it comes to nomenclature, I believe at the end of last class might have been where it came up. People were like, oh, you know, I love, what was it, Dave? Was it Dave? No? Okay, so it wasn't Dave. There's like the organic chemistry tutor, Dave, I think is his name. I don't know. Goofy guy, beard, mustache? No? Okay.
His name was Rob.
Oh. Not in the tutoring center YouTube videos. So if you're looking at YouTube videos as supplements, those are fine. Just, again, be careful when coming at nomenclature because you can see all sorts of varying layers behind them. Okay, so it can get complex really fast. So if they drop a structure, drop a name, you're like, whoa, hold up. That was probably too much. Don't look at that. Avoid it. Go somewhere else or send me an email. Hey, at minute 3 in this video, they put up this name. Is that something you expect me to do? And I'll look at it and be like either yes or no. Ideally no, right? But we'll see. So definitely take advantage of whatever other resources are out there. You're welcome to do so. Again, I just want you to be careful that those videos are not built for this class. What they are built for is a full year class. Some of which we cover, some of which we don't. And so finding that blend between those is going to be potentially problematic. Okay? So within the video, were you guys okay with this? Did you guys understand kind of the differences? Note that all 3 of these compounds, that one doesn't have. Oh no, never mind, different thing. That the first 2 compounds both had C4H10, were both 4 carbons, right? Would we call them the same? Okay, that becomes an interesting kind of dilemma or question. I would say you should not be calling them the same or identical. Why?
Because, like, molecularly they're different.
How? Yeah. What do you mean molecularly they're different?
The molecule is shaped differently,
Okay.
even though it has...
I accept shape differently. How about this red one? Is the red one molecularly different? Because it's shaped differently, isn't it? Right, and this is it becomes hard to nail down the language behind it, and that's the part that we're trying to kind of nuance and get at for these definitions. If I draw this red one, all that's happened for the red one is that I rotated that sigma bond. Am I allowed to rotate a sigma bond? Yeah, sigma bonds I can freely rotate. It's the double bonds that I can't. And the sigma we can rotate because they're s orbitals and they were direct overlap. At all rotations, they overlap. Only the pi bonds, because they're indirect overlap, can't allow rotation while maintaining the bond. Okay? So because they're all sigma bonds, I'm allowed to freely rotate. But could I freely rotate this in any possible way to get this to happen? No. Okay? And what's happened here is I've taken this carbon and I've changed the connectivity of the molecule. Instead of that carbon being connected to, say, carbon number 3, I changed its connection to be carbon number 2. I've changed the location of a sigma bond. Okay? So that now changes some of our interpretation behind it. So our starting structure, left structure, and our red structure, we could now call identical because for the most part they are. There is another definition we can worry about that we won't. We'll call them identical. Okay? Their formulas are the same and the structures are superimposable. What does it mean to superimpose? Right? Common, oh, I just overlap my hands, right? They're superimposable. Your hands are technically not superimposable. When you overlap your hands like this, you're overlapping the bottom technically with the top of your other hand. Okay? So your hands aren't superimposable. But if you take, because they're right here, a paper clip, way to pick something insanely small that no one can see, you could overlap paper clips so that they would superimpose. So superimpose means all parts of the two things you're moving around would perfectly occupy the exact same space. So you take your two things, make one of them a ghost, and put the other one inside it. As long as everything perfectly aligns, they are superimposable. There's another word that's superposable that means effectively the same thing, except one's not a ghost. You're just putting them close to the same space. I'll use them interchangeably. For this red molecule, it doesn't look superimposable because the bond doesn't perfectly align, but we have to acknowledge the three-dimensional aspect of our molecule with sigma bonds allowing it to rotate. One of its rotational states allows it to superimpose. They are therefore identical. Okay? Isomer, they have the same formula, but the structures are not superimposable. So there's no possible way I can take this middle molecule and have it superimpose either of the outsides. It's not physically possible. Okay? That superimposability can have a couple different manifestations, and we'll look at that as we kind of dig probably into Unit 2, the next unit. I don't think we'll talk about that this year. It's on the schedule to talk about. We'll see. Okay? So these two are isomers of each other, and if we cleared the screen and brought back that other structure, this structure is now different from both of them because it does not have the same formula because it has 5 carbons, not 4. Make sense? So we're now trying to define the relationships between structures while also taking into consideration what we understand of everything else. Right? And what we're starting to manifest is this kind of goofy flow chart. Where that previous slide ended was right here. We have isomers, different, and identical. I said that isomer could be further segregated. We could look at the atom connectivity. The atom connectivity we just talked about. Was the methyl group located at the exact same atom? No, in one case it was at atom 3, the other case it was at atom 2. So I changed the connectivity. If I change the connectivity, that's a structural isomer or a geometric isomer. If it has the same connectivity, they're now stereoisomers. For that particular example, we can't look at stereoisomers. We'd have to make our structures more complex. Okay? So, before we start getting them more complex, what we need to start thinking about is how we look at our models. Okay? So, what I've got here, and you guys will have to figure out how to share amongst yourselves. Might make you move. You guys can kind of float in the middle. Well, I gotta put 2 molecules outside. What we've got here, I'm kind of picking the center of mass, so you could probably jump up. What you guys have is ethane in your hands. So 2 carbons with all the 4 bonds shown. We could look at methane. Okay, methane gives us all our bond angles, all that fun stuff, and we just have a representation. Okay? We drew that representation with wedges and dashes, and we are happy with it. When we scaled it up to ethane, things get a little bit more complicated. And if we were to draw out our Lewis structure, we could get something relatively simple like this, which has hidden some of the information. We could add that information in by saying wedge and dash. And we could say wedge and dash, yeah? Okay. What if I had instead said wedge and dash, but kept the other side the same? Is that still effing?
Yeah.
Yeah. All that's happened is I've done a rotation. Is that rotation obvious?
Yeah.
Okay. Some people are like, yes, that's obvious. Does it matter?
No.
Okay. And this becomes the challenge and why we introduce different viewpoints on our molecules. Okay. So if we were to go through and take a look at this, what this is now asking us to do is take that model, and now instead of looking at it from the side where you see both carbons, is to turn it. Turn it so that you look at it end on where you only see one carbon. Okay? When you look at it end on to the point where you can only see one carbon, okay, what do you see? Everybody has the exact same molecule in front of them. Draw out what you see.
CH3.
That's words. You should draw it. Does anybody see what I've drawn up on the board?
Yeah.
When you're looking at the model, does anybody see that?
No.
No, why not?
In order for it to stand, you have to have the two hydrogens on the bottom.
That drawing that I've shown doesn't make physical sense for what you're looking at, right? Because they would then have to be perfectly balanced on the hydrogens. Does that make sense? So the point here isn't to say that this is a wrong drawing. The point is here, I want you to draw exactly what you see. Like, that's the point behind this process. Okay? So if we do that, theoretically, what we would see is something along these lines. Okay? And you'll note that when I draw this, and the way most of you drew it, you drew those all as solid lines. What did solid lines mean? They're all in the same plane. Are all of those bonds in the exact same plane? No, in fact, none of them are in the same plane. Okay? So this change in our molecule could mean that we have to now go through and show wedges with all those. Do you really want to go through and do that? No. So what do? We just say we've changed our orientation on the molecule to create a new viewpoint, and in that new viewpoint, it is assumed that those are all wedges. This way we don't have to worry about it. Okay? So that means we also have to acknowledge that this is now a new viewpoint on the molecule, and because it's a new viewpoint, we now have to name that viewpoint so everybody knows what we're talking about when we're talking about that viewpoint. This viewpoint is known as the Newman projection. Okay? So if you saw questions in the homework about Newman projections, this is what we're asking about. It's the end-on view of the molecule. Okay? In all of your drawings, nobody drew anything happening on the back atom, as far as I could tell. Why not?
It's pretty much right behind.
It's right behind. It's hidden from your view. It's not easy for us to see. But it is still there. Okay? And it could have a manifestation for us to deal with and interpret. So what are we going to do? We're going to make sure that we can draw it in there. Right? So what we could do is draw a slightly larger C in behind it so we could see it. And then we could draw in the bonds that are overlapping it, right? And God, that would look really awful and ugly, okay? But we could do that. So now what I would like you to do is take any one of your carbons, either one, okay? And I want you to rotate the sigma bond 180 degrees. Yes. Hold that. Rotate. Yeah, well, yeah, keep going, because we said 180. It was a bit silly to say 180, but that works. There it is. Ta-da. You've now done a rotation of 180 degrees. What happens when you look at it now? If we were now to go through and do that exact same drawing, we're now going to potentially run into some issues, because that initial drawing that I had where the carbon had the hydrogen straight down is now possible, because the back one could act as a stabilizer for it. Okay, so we could look at it in this fashion with our C in the back. Yeah, does that make sense? Everybody kind of getting it? Okay. Or if you were going to be contrarian, which is fine. It's not like you're trained to be contrarian by your instructor. We could see something like that. Everybody kind of see it? Okay. The new structures that we just drew, would we expect them to be different from each other? I know it's a really weird, vague question. Okay, no. Would we expect them to be different from the first structure?
What was the first structure?
The first structure is the one that I've got drawn above table.
I mean, the bond is rotated, but it's all the same stuff.
So it's all the same atoms. So according to our definition of different, we would say that it's the same, no big difference. But would you really call all of those identical? Do you have anything in your body saying those aren't, I don't like those being called identical? There's something that looks a little bit off, like they don't look the exact same drawing. According to our definitions, yes, they're absolutely identical. It just doesn't quite fit that. There's something a little bit weird here. That something that's a little bit weird there is a good reflex. So let's push on that a little bit. What do each of those lines represent? What's a bond?
The sharing of electrons.
Electrons. Do electrons like being near each other?
No.
No, what do?
Repulse.
They repel away from each other. So if we're now looking at these two sets, we've got our table drawing and our box drawing. Do you think they're the same energy? No. Which one do you think is different and why?
Different. Like,
Pick any difference you want. Okay, we said they're different. How are they different? What's that? Okay. How are they different in energy? You're saying they're different. That means one's high, one's low. Which one's high, which one's low?
One's closer to the other, one's further away.
Those electrons on our table drawing are close together. Is that a good thing?
no.
No. That makes the energy of that structure higher energy because they don't want to be there. What do they want to do? Well, they want to get away from each other. They can't pull backwards away from each other because they're connected by that sigma bond between the carbons. How do they get away from each other? They rotate about that sigma bond to get us the alignment that we've shown on the right. Okay? So what you've just identified is a high energy rotational conformer and a low energy rotational conformer. Fantastic. Good job. Okay? And all that's coming from is just looking at the three-dimensional model and taking some of those same rules that we already knew about electron repulsions and predicting how those things would scaffold out. Okay? Does that matter? Yes and no. Okay? In the vast majority of scenarios, it isn't that big of a deal, but when we're looking at raw energies of our molecules, it does manifest in certain particular fashions. Okay? So let's try and see what's going on with that. First and foremost, the drawings that I drew look kind of ugly, right? With all the C's over there. So we want to move to an accepted drawing system. The accepted drawing system is what we're seeing down below. What we're seeing down here is exactly what we had on the previous slide, except these are now prettier computer generated. Okay? We've got what you all probably drew for our table drawing here, our initial table drawing, okay, where all the bonds were overlapping. The back atom, that big red C that I showed larger, is that circle. So we have a reverse perspective on this. The atom furthest away is drawn the biggest so that we can see it. If we made it the smallest, it would be behind the front atom and we'd never see it. So we have to pull a reverse perspective. The front atom is a little dot in the middle. That back atom, and if we color code based off how we did it before, that was front. And then our back atom out here is the red one. Note the hydrogens connected to the back atom just have the lines going to the circle. Why? Because they're connected to the back atom. They aren't connected to the front atom. The front atom just has the lines, or has the lines connected all the way through to the very center. When we did that rotation, what happens? Right? Well, what we've done here is taken that front carbon and we just turned it. Ta-da, we get this. And what we're establishing now is a high energy state and a low energy state. Because we now have different energy states and they have different kind of meanings associated with them, what else do we bring into it? Everybody's favorite, names. When we look at one, we now have to name what it is. And the names that we get for these, fans of Twilight? No, too soon? Eclipsed. This one's not Twilight, as far as I know. And staggered. Okay? Those are now different energies. We can continue to do a rotation and we should see the energy oscillate back and forth between our high energy state and our low energy state. Okay? With ethane, it's rather boring and simple, so what, of course, we're going to do would be make it more complicated, and we would move it up to butane. But I believe we're done, right? Are we done at 15? Yes. So with that, we're going to be done. We will take a look at butane on Thursday. Once we move through butane, that's going to give us enough context where we can actually look at everybody's least favorite, chairs, which is cyclohexane, so we can see how this manifests into rings. And then we'll probably get to talk a little bit about chirality, which means chirality is not going to be a huge part of the exam next Thursday. But I'll test on it a little bit. Okay? So I think we're okay. I still feel like I'm talking too slowly, unfortunately, which I know some people are upset with because I think I'm going too fast already. But I think we're at a decent moving pace. Oh, no. Okay. Ooh.